In section 5.4, we will describe a new theorem about additive property of definite integral. So this property basically says that if you want to find the area underneath a curve going from one point to another point called C, then you can basically do that job in parts. You can find the area from A to B first, then find the area from B to C next, and then add them up together. As long as B is somewhere in the middle between A and C, you're basically fine and you're all right with that. Why would we need this theorem? We need this theorem for problems such as this one over here, where the function has different looks depending on where the x is. So let me go ahead and graph this problem, and we'll talk about what the graph is basically doing in this problem and why we need to talk about the additive property of definite integrals. So we begin with the xy plane, and the graph of this function f of x is going to be what we call a piecewise defined function. It's going to be kind of funky looking. It basically is 9, so it's basically a straight horizontal line for any x that's less than 3. So if x is 1, we put a 9. If x is 0, we put the graph at 9. If the x is -3, we put the graph at 9. So anytime you're before the number 3, your graph is always the same. It's always a 9. So let's pretend like 9 is over here. This is what the graph looks like as long as you're before 3 itself. Okay. By the way, even at 3 itself, the graph is not even 9. It's just, we don't know. This is the reason why we need the second part of the graph, which is x squared. So anytime your number is more than 3, the graph should be the graph of x squared. So if you're 4, 4 squared will be 16. If you're 5, 5 squared is going to be 25. As a matter of fact, if you're 3 itself, you're allowed to use this equation to compute the value. 3 squared would be also 9. So remember, 9 was this line right here. It's on the y-axis right there. And afterwards, the graph looks pretty much like a parabola. So this is pretty much the graph. And at 3 itself, the graph is a solid 9 because of the x squared. So this function f of x has what we call a piecewise function graph because it's got two pieces, one on the left, one on the right. And in this problem that we're looking at, we are searching for the area from -4 to the number 5. So -4 is somewhere around here. We want to know the area from -4 all the way to the number 5. So obviously, as you can see, the graph is kind of a rectangle at the beginning, and it's kind of a weird looking shape at the end. And so we need to use the additive property to be able to find the complete area. We have to split our job into two parts. One part where we find the area of the rectangle, the second part where we find the area of this region after the number 3. So to find the total area, we need to combine the yellow area plus the blue area. And since the graph changes, we need to do two different integrals. So the total area that we're looking for, or in other terms, the integral from -4 all the way to 5 on this function f of x dx cannot be done in one shot. It has to be done in two parts. It has to be done from the part that goes from -4 to 3, and 3 is the border point under the function f of x. And then we have to do another integral from the border point 3 all the way to 5 on this function f of x dx. Okay, so the first integral represents the yellow part. So this integral represents the yellow region, and the second integral represents the blue region. And 3 is what we call in these problems the border point. So discover what the border point is. That's where one graph starts and one graph ends. And that's going to be the point that you put on your integrals. Okay, so that's important. Keep track of that. And at this point, let's see. What do I put in place of the function f of x on the first integral, the one in yellow? So the integral in yellow has what kind of look to it? It has a horizontal look, and the equation for that was 9. So that's what we're going to write in the first integral. Whereas the second integral, the blue one, was going from 3 to 5. What did the graph look like on that integral? The graph on that integral looked like a parabola, and the equation for that was x squared and then dx. So basically, this problem, instead of doing one integral, we're doing two different integrals. And so you got to be careful with each of the upper bounds and lower bounds. So let's start with the first one. The antiderivative for 9 is going to be 9x. And that integral is going to take the numbers -4 and 3. So it's going to have its own upper bound, its own lower bound. Then we have to do an integral for x squared. What's the antiderivative for x squared? It's x cubed over 3. And that integral is going to be between 3 and 5. So its own upper bound, lower bound. So let's go ahead and plug them in. Okay, so the 3 goes in first because it's the upper bound. We get 9 times 3. Then the 4 goes in after. We get 9 times -4. Okay, so all of these guys are the answer of the yellow integral. So far, so good. Now, there's a plus in the middle. I'm going to put that plus right there. Then, plug in the 5 for the x. Plug in the 3 for the x. 3. And those two numbers that I just wrote represent the answer of the blue integral, or in other terms, the answer of the second area of the problem. And at this point, I am ready to put everything into the calculator and just get the solution, get the fraction or whatever. The answer turns out to be 287 over 3. I'm pretty sure you're wondering if there's a way to do this with a calculator. And then the answer is yes, there's a way to do this whole thing with a calculator. You just have to be careful how you type this function into your calculator. But once you type it correctly, then everything is going to be fine. So what we're going to do for calculator is this. We're going to go to y1 and we're going to type in the first equation inside parentheses, then the condition. The condition is the part that's written right there, x less than 3. Then we're going to put a plus sign and we're going to type the second equation with parentheses again, and then put the condition next to it. The condition is x is greater than or equal to 3. So let me show you how we can plug all of these things into the calculator. And once you plug them all into the calculator, then you can use the same kind of command features that we did before to get the area underneath the curve. Okay, so here we go. First, typing the 9 inside parentheses, and then the condition x less than 3. How do you find less than on this keyboard? You have to click this. Second, then math. That gets you the less than, greater thans, and whatever. Less than is option number 5. So you can go down with your arrow 5 times in a row, or you could just click 5 on the keyboard and you get it on your screen. So the condition is that the graph is 9 as long as you're less than 3, but the graph is something else after. So we're going to put a plus, and then the second equation, which is x to the power of 2, when the x is more than or equal to 3. So x is greater than, so I'm going to go second, math again, and then greater than or equal to is option number 5. So click 4 on your keyboard, sorry, option 4, click 4 on your keyboard, and then you're just basically finished. Close the parentheses, and I'm going to go zoom 6 to make the graph look nice and pretty. So you can see the graph is horizontal for a while, and I'm not really seeing what's going on right there. Let me change the settings a little bit so we can see the whole graph. We don't have to change the settings, but I'm going to do it anyway so we can see a little bit more of what's going on up above. So I'm going to change the y minimum to be, let's say, -2. The y maximum, let's say 25. You'll see the graph, again, straight horizontal line, and then a parabola afterwards. Okay, let's go second, calculate, and we're going to do 7 to find the integral, or the area, from -4 all the way to 5. So we're going to click lower bound is -4, enter, and then 5, and then enter. The calculator highlights the area for you. It's the yellow space plus the blue space that we were talking about earlier, and it tells you the solution is 95.66. So it's not an exact number, and there's no way to get the exact number on this screen. This is the reason why you have to do the work by hand to get the exact solution. And I'm pretty sure MyMathLab wants an exact answer, so that's why you have to do all the work by hand. Now, if you know how to set it up and get this, then you can do that setup and plug it into the main screen of the calculator, and you'll have the right answer still. So here's what I'm talking about. Let's go ahead and go to the main screen of the calculator. So quit this, and then just type math 9. And so we're going to type in the problem, basically. The integral, the first integral had 9. It was integrated with respect to x, and the bounds were -4, and the border was 3. And then we had another integral. So again, math 9. And the second integral had x to the power of 2, We integrate with respect to x from the border point 3 all the way to 5. And then if you click enter, you get the 95.66 that we saw on the other screen. Or if you click math 1, there it is, 287 divided by 3, which is what we predicted over here. So it works out. So again, you've got two different options to plug in the problem into the calculator. Either one works. Just figure out which one you like and do that one. So I want to give you a chance to try this next problem, and I'll explain how to do it in the next video. So in the meantime, try to find the area that we're talking about here.